So he said so. The guy.
Oh, he's watching.
Yeah, he's watching. They push the button, and then it says that it needs some second to.
So that's the big brother. The big brother.
The big brother. Yeah. I know it's a little bit strange.
Last year wasn't it the same?
No, last year was automatic, but they make an improvement. So when you start, it starts recording. And now they have an improvement. It starts recording after. Now this is recorded, so you see, it's a recursive operation. Okay, so at the end today we want to finish this object and say this thing to say that at the end that the measure with the sets of measurable so the family of measurable set is a sigma. No? So the last thing was that union of counters. So if I remember well, was that we have this proposition. So if EK is disjoint, is finite, is a family finite, and disjoint, and EK is measurable, then, okay, we have the separation for all A, the outer measure of A intersection, the union, so the partition into this set, is the sum, the measure of A intersection with A. So the proof was pretty much fine because you need just to do by 2, and then it's just the application of the measurability. So let's see, just to warm up. A intersection E1 union E2 by measurability is M star A intersection E1 union E2 intersection.
Should this be M star?
Yes.
This one, yeah, yes. Yes. And then I need those to close the parentheses. Otherwise the sentence is not correct.
I think we did this last time.
Hmm?
We did this last time.
Yeah. I just warm up.
Okay.
Just to wait the 15 seconds. And start of A U1 union E2 minus U1, and then okay, you just do what is the thing because then this is the sum. Okay. Okay. So what we have now finally together, all the thing together, we have that. So we have proof. So the mark so far R is measurable, or the empty set is measurable, which is the same. So if E is measurable, it's equivalent to the R minus E is measurable. So let's say E complement, the complement of E. In order to have that. And then EK finite. Okay, finite and okay, here is this joint, it doesn't matter. Finite measurable, finite family of measurables, measurable sets, then the union of EK is measured. Okay? Because we have done that. Well, if you remember, we have that the union, the intersection was, the union of two sets is measurable, the intersection of two sets is measured because you have the complement, And then, okay, you gain that even if they are not disjoint, they can be written like a disjoint union of intersection of sets, no? One minus the other. So at the end, okay, we have this guy which implies, so the Lebesgue measurable sets. And okay, let's put a notation here that you usually find in the literature, measurable sets. And this is called usually R, L, and okay, is analogy, at least. Okay. So today we prove that it is a sigma. And then we go on, and if we are lucky, we end up with something very crazy. So some very strange set. Okay. So the if K now is countable. Family of, okay, here I can take this joint as usual, because being an algebra I can add without loss of generality. Sets. Then the union of K is enough. Okay, so it's always difficult to restart, you know, after the afternoon. I believe is even more difficult than in the morning. Morning is fine. Okay. Proof. So I have to check the stuff, no? So I have to check that M star of A for all A, M star of A is equal to M star of A intersection the union plus M star of A minus the union. Okay. This is what I have to check. Okay, I have to check. I know that this holds if I fix M here, up to M, no? M star of A is equal to M star of A intersection the union to N of E K M star of A minus the union up to N of EK. And certainly now, first inequality, monotonicity. So here is I subtract a larger set. So this guy is larger than when I subtract this set. Okay? And here, well, I have the previous proposition that is exactly the sum of the measures. So this is greater or equal than the sum M star A intersection EK up to N plus M star of A minus the union up to infinity of K. Okay, it's okay. I just use the previous proposition here, and here I use the monotonicity. And now this, I observe that now the N is free. No? So being free means it also any N, and so it also when I take the sum of the series. So this holds for all n, and this implies that m star of A is greater or equal than the sum up to infinity m star of A intersection k plus m star of A minus the union. And now I just want to, I would like, so compare this guy with this guy. So let me subadditivity.
We know that this is
This
smaller than this.
This one is
Smaller than this.
smaller. So I get that this is greater or equal than this sum.
Yes, yes.
Am I done? Yeah, because the other is by definition of outer mesh. Okay?
So I have this the same as this.
This one is equal, no?
Okay.
And this one is so let's write this set. This is the union of the k, A intersection k.
Okay.
And
Okay.
n is subadditivity. Okay, so far so good. And if they are not disjoint,
What?
if the k are not disjoint,
We can disjoint files.
yeah, because I just if I have fk not disjoint, I do the proof with pk equal to fk minus the union up to k minus 1 of fk. And then, I mean, the formula holds for fk, but the union of fk is equal to 2. Okay, fine. Oh, so, very happy because now we have proved that the measurable set is a sigma algebra. Oh, put this like this should be a theorem, but actually it's a corollary, but not a theorem. So L is a sigma algebra. So I'm very happy, but there is something which doesn't make me so happy, unless I prove that this algebra is not small. Because so far, if you remember, I said that R is measurable, and then the empty set. So why it could be only the sigma algebra?
The trivial sigma algebra?
Yeah.
It is not, because it has the intervals.
It didn't prove it yet.
We proved that the intervals, the open intervals are measurable.
I don't know, because it's written here.
This one?
Maybe I did something earlier. It's just we proved that the interval has a length, the outer measure is equal to the length.
Yeah, we proved so we proved that the intervals are
Yeah, so it means that it is really an extension of.
Okay, but we proved that that a set of measure 0 is measurable.
Yeah.
So phi is
Not a trivial. Yes.
So the algebra is not 20.
But then there are, you can only have set of measure 0 or set of measure infinity.
Yes.
Okay.
And still it's not fine.
Yes.
I mean, it's
So
a
we
little
need
bit.
something in there.
You need that, well, but being a sigma algebra is important because once you have a set, you start with that, or a family of set, you start from that set and then at least it contains the smallest sigma algebra generated by those sets. So,
Which sets?
now we have to find, at the end we need the open sets.
Sigma algebra.
So let me open this parenthesis here, because this is very general. So once you, well, this hold is a proof that holds, if you check, doesn't matter if you have the Lebesgue outer measure. No? This works automatically because there are only sets operations, subadditivity and monotonicity. So automatically, you give me an outer measure on the power set, and then you get a sigma algebra and a measure. So the trouble is, which is so to characterize the sigma algebra. No? So for example, this is not in the note, but maybe it's time to discuss it. So let's take let's say mi star of a set A is equal to 1 if x is in x bar, a fixed point is in A, 0, x bar does not belong to A. So it's like the function evaluated in x bar. Okay. So is this an outer measure? But okay, this is quite easy, no? Because so let's say mi star, I have to prove that well, the empty set is outer measure 0, and mi star of the union of A. So if this is 0, there is nothing to prove, because I have to show that let's say for any, even uncountably many sets. So mi star of the union of any set, if it is 0, is certainly less or equal than any sum. If it is 1, means that it is inside one of the set.
Yes.
Okay? So whatever is the meaning here, well, the meaning is that this is bounded only if this is one only for finite
disjoint A alpha, but if it is not disjoint, it should be less than
less or equal, yeah, correct, yes. So if it belongs to one set, in this sum at least one of the elements is 1. So certainly is larger than 1.
I have a question that's not related to this. How do we, if we have a family, countable family of disjoint measurable sets, non-disjoint, they could be disjoint.
Mm-hmm.
How do we get, if we have a countable family of sets, how do we make them disjoint? Or how we partition them into disjoint sets?
So F0 becomes, let's say F1 becomes E1. F2 becomes F2 minus F1 equal to E2.
Oh.
And then, okay, just this formula is the set minus the union of the previous one. Okay, so it means that it's an outer measure. Now let's prove which sets are measurable. Okay, so mi star of any set, let me versus, I don't know yet what to put here, mi star A intersection E, mi star A minus E. Okay, if X is not in A, it cannot be in the two pieces. If X is in A, it's just in one of the two.
Yes.
So any set is measurable. So if you start with the delta, this is the, so mi star is actually a measure on the power set. And actually it's the Dirac delta, no? This my mi star is equal to the Dirac delta in X bar. Okay, you see, I found the sigma algebra. It's very easy. The whole power set is the sigma algebra of my measure. Well, on the other hand, I can do something.
But can we get an outer measure whose the sigma algebra of measurable sets is the trivial one?
Let's do that. This is not in the notes, I'm sorry. Just I prefer to put this point so you appreciate the next result. So let's say mi star is equal to 0, mi star of A. Is equal to 0 if A is the empty set plus infinity otherwise. Okay? So clearly the only case to prove is plus infinity, but if A is not empty, And then it is the union of quantum remaining set, at least one set is not empty, no? So clearly Mi star is outer measure. Now let's see what are the measurable sets. So Mi star of A should be equal to Mi star of A minus E plus Mi star of A. Okay, plus infinity actually is a bad one, because then becomes infinity. So let's put it well. Yeah, which works the same, no? Because plus infinity is plus infinity plus infinity. Okay, so here. So which sets are measurable? You're partitioning A into two parts. And
so if it is not empty, then one of them is not empty.
Both of them. So it's 1, 1, 1. So the only measurable set is equal to X, or the whole set. Let's say. You don't have resolution to see anything else.
Sorry, but if A is not empty, then we only have that one of these are
should be empty. One should be empty. If A is A, this should hold for any A. So it is empty. Well,
no, we take A not be empty and show that this cannot be equal.
Unless E or the complement of E are empty. If E is empty, this is 0 because it's empty, and this is A. So it's 1. If E is the whole set, this is empty, and this is 1. So let's see 0. Okay, so the sigma algebra here is really the trigger one. The empty set and R. So the point of the theory is to prove that actually you have something which is non the trivial one. Okay, so let's see that the segments, so I erase now. So the segment AB is in the sigma algebra of the Lebesgue measurable set. Okay, so let's do a slightly faster than the book, because so the various step is that first, just consider A plus infinity. Why? Because the sigma algebra generated by this set contains any interval. Simply take the complement, and so the intersection is that. And so if Ik is a covering of A intersection A plus infinity, then Ik intersection A plus infinity, so open covering, of course, because I decide to use open sets. It's an open covering of A intersection A plus infinity. Okay? Which means essentially that the outer measure of this set can just be computed by taking covering inside this open section. This is we already used this fact earlier. The same for A intersection minus infinity A. Okay? And okay, let me say something. And finally, and there is something in between, but we are going to have fun. Finally, m star of A minus the point A is equal to m star of A. Okay. Okay, so there are some gaps, of course. These are just the pieces that one sees these pieces and then decide how to put them. So let's put a little bit the arrows with the implication. This is just for fun. Okay. So first of all, is this sentence correct?
One conclusion is obvious. But
Yes, clearly, yeah, clearly. So let's do the proof of this one. So clearly we have to prove that m star A minus, well, this guy is less or equal than m star of A. This is trivial. Now take a covering of A and
it covers also A minus. If we subtract A from every element,
it's already written here. Restrict half on one side, half on the other side, and then you take just a small epsilon covering the segment. Is another covering, so essentially this is an A covering of m star, of A, sorry, which is made by a covering for m from this part, a covering from this part, plus 2 epsilon. Okay, so let's do it. Well, then take ik intersection A plus infinity, IL intersection minus infinity A minus epsilon, A plus epsilon. Okay, so, well, the only interesting part when this is no is finite. No, this is finite. In that case, this covering is larger.
I think this IK should be a cover of A minus the singleton A.
No, if you give any covering, I just can restrict the covering outside and outside. Well, it's the same at the end.
Yes, but because we want to prove the other inequality, so we want to prove that any cover.
Yeah, can be, yes. Well, yes, it is fine. Yes, take a covering of. Yeah, let's do this way. Yes, I was thinking the other. Yeah. Oh. Yeah, because we need to have the inequality. So if, let's say, IK cover A intersection A plus infinity, or IK cover A minus the point A at minus epsilon, A minus epsilon, A plus epsilon. And then, so that for this covering of A star, we have the sum of M star of IK plus 2 epsilon. Okay, is larger or equal than M star of A, and this guy over here is okay, up to another epsilon is M star of A minus the point plus 3 epsilon. It's a little bit not straight, but usually when you have to build a proof, it's not straight. No? You understand the pieces. Okay, are you fine with this one? So let's put it straight. If this is plus infinity, there is nothing to prove. Otherwise, there is a covering such that the outer measure plus epsilon is larger than the sum of the covering. And then I add that is interval, so I have that 3, I add 2 epsilon to the covering, so I have 3 epsilon larger than this guy. Then for any epsilon, I'm okay. So let's cancel this point. Well, we keep it. Oh, okay. So now we have that. M star of A is equal to M star of A minus this guy. A minus this guy, you see from this observation, if I take a covering of A minus this guy, I can just intersect and I get two disjoint coverings, one for the right part and one for the left part. And being an intersection, the sum of the length is less or equal. Okay? So let's cancel and fill it.
Sorry, haven't we proved that the measure is additive over disjoint sets?
If they are measurable.
If they are measurable, so we have A is measurable and the singleton is
But
measurable.
A is not measurable. It's okay because they are measure 0.
A is not measurable.
But as measure 0, then it's out.
Oh, okay.
Indeed, I think that we can do something even better because this was the proof, but actually there is now I see another proof that is larger. So M star of this guy is less or equal than M star of A minus the point plus M star of the point. And that's it. It's even faster. I mean, we were just proving again this fact.
Yes.
And this is 0.
Nice.
So we can even do for countable.
Yeah, if a set has measure 0, it works. Yeah, I think it's what I needed. I think, on the other hand, I just brought this because it was 3. Okay, so we have this. And now, how to fix this guy? So if, okay, K is a cover of A minus A, then the two disjoint covering K intersection minus infinity A union IL intersection A plus infinity is a covering such that now I'm asking you what happens to, well, certainly I have that. So the length, the sum of the length of I, K plus the sum over the length of IL, it's equal to I so of the original, sorry, I'm not the notation, I'm not fine today. So the sum over K of the length of this intersection plus the sum of the length of the second intersection. I'm saying that this is equal to the sum of the length of the initial intersection. Because you see, I remove 1 point for an interval.
Yes.
Okay, and from this guy, what I get that, well, so we can conclude here.
But we don't say that the length of the interval, we say the outer measure of them, because we have the length only of an interval, but this is now not necessarily an interval.
Which one? This one?
Yes, for example.
If this is an interval?
Okay, sorry. Sorry.
Okay, so let's finish. So essentially, if I have a covering which gives the measure m star, I have another covering which gives with the same value, which is for the two sets. And then I have the m star. So it's the infimum is larger or equal. So let me say it. So because it's so fine to. So okay, so this sum is larger or equal than m star of a intersection a plus infinity plus m star of a intersection minus infinity a, because this is a particular covering. So I get that for any covering of m star of a, the length, the value is larger than the sum of the two quantities. So I get that m of a, m star of a is larger or equal than m star of a intersection minus infinity a plus m star a intersection a plus infinity. And now, well, I know that this guy is equal to the same set when I add the set of measure 0.
Yes.
Set of measure 0. So this is equal to m star of a intersection. Okay, I add here minus infinity a, m star a intersection a plus infinity. Because m star of a of the point a is equal to 0. But this is exactly the thesis, no? Because this is the complement of this set. Oh. Okay, so now let's collect the thing here. So we have that L is a sigma algebra. L contains all the open set, which is the topology, no? So it's a sigma algebra, it contains the topology. And now you have this set theoretic operation, which is the following. So given, let's say a family, let's say C containing the power set of R, let let's say, okay, here let's say C, I want to change the, okay, let's say C, let's say D, be the smallest sigma algebra.
But excuse me, but it doesn't contain the topology because it is sigma algebra, because of this specific property that every open set it is a union of countable many intervals.
Yeah.
Because in general it could.
But actually, yeah.
So it is not only that it is sigma algebra. We need this additional.
That it is a separable space.
Yes.
Indeed, that's why. And indeed, the measure theory works in separable spaces. The moment you exit separable spaces, you cannot prove anything. Well, you can prove something, but it cannot be decided even. Because it's as usual with what you can construct, and the theory is constructive is only using countable many operations. So finitely many and pass it to the limit. And in uncountable many sets, there are questions which cannot be answered. I mean, they cannot be decided. So yes, it's usually like this. Always countable many. So the smallest sigma algebra.
But isn't R squared, for example, separable and doesn't have this specific property?
Who?
R2. Isn't it separable? It is separable.
Yes,
but
the base of the algebra.
Yes.
The base of the topology.
Yes, but it doesn't have this particular property that every open set is a union of countably many open set.
Yeah.
It doesn't.
If the base of the topology is countable, for sure.
Yes,
If the base of topology is generated by countably many sets, the union of any family,
yes.
But then it's, since you have only countable many sets,
Yes.
so the neighborhood are uncountable,
Yes.
but the open sets, yes. So the sigma is contained, containing C. So if you give me a family of sets, I can just find the smallest sigma algebra containing C. No? And it is the intersection of all sigma algebras containing C. So this is the set theoretic operation, no? So give me a family of set, take all the family of all sigma algebra containing C and take the intersection. So the operation is meaningful simply because power of X is a sigma algebra, or power of R is a sigma algebra. So I'm not intersecting on an empty family. At least there is one sigma algebra. Then, okay, you can have several many, and then you take the intersection. And moreover, this is an exercise if, let's say, D1, D2 sigma algebras, then D1, D2 is a sigma algebra. Well, this is very easy, no? Because they are close with respect to the same kind of operations. So if you take two sets which are in both, then whatever operation you apply, you get another set which is in both, because they're closed. So, very clear. So this small sigma algebra is usually called like the sigma algebra generated by C. Okay. So let's apply the definition here. There is an important sigma algebra is that so the definition, the Borel sigma algebra is the sigma algebra generated by the topology. And this is the most important sigma algebra. And so we have the following corollary. Finally, L contains the Borel sets, which means that all the Borel sets are Lebesgue dimensional. There is a way to construct explicitly the sigma algebra given a family of sets. And because essentially the idea is that, well, I have these operations. I can take complementation, intersection, countable union. Okay, so let's start doing that. So I'm putting a picture that just to make you feel what you can do. And this theory is called is the descriptive set theory. So so here is a non-descriptive set theory in the sense that you know that these are measurable and you know they are sufficiently many. So one result we will see is that a Lebesgue measurable set is a Borel set plus a set of measure 0. But if you don't have any measure and then you want just to study the sigma algebra as an algebra of set, the Borel sigma algebra as an algebra of set, maybe you want to know which elements it has. So this is just a remark. How to generate in Borel, but in general any other algebra. So the picture one has in mind is the following. You take here the open set, and here you take the closed set. And now, which operation is in the algebra which make me exit from the open and closed sets?
Which one?
Which operation are in the algebra?
Intersection.
Countable intersection. And did I say what is the name of the countable intersection?
Yes.
F
sigma.
F
F delta. Sigma G delta. G delta. G delta sets. From closed, countable union. So let's say this one is intersection. So intersection, let's say, and here is union. F sigma. And well, unfortunately, if I take the countable union of G delta, is not a G delta. Because if you switch, well, you have you cannot switch and have countable union operations. So here we take the union, and here we take the intersection. Clearly, the thing is that when you do the complementation, you see I keep track of the complementation, no? It's always, because the complementation switch the operation, then switch the set. So when you got the complement, and then how many times it should go on? That's the question.
Infinitely.
Infinity, but which power?
Which one?
Countable many
Countable
times, just
infinity.
n fixed by n.
Yeah, count many times, but actually you see there is an ordering here. So you do for any countable ordinal number. So if you give me an ordinal number, a countable ordinal number, then essentially you do this operation, start from a family of set, and you do this operation until you end up with a set. So we have to do that. Because it's not like n, it's really an ordinal, or it is for all omega ordinal countable, let's say ordinal number with cardinality less or equal than m. Or let's say like this, strictly less than aleph 1, the first uncountable.
You mean we do this for every countable
Ordinal
ordinal,
number.
and we take the union of all of those?
And the union of all of these family sets is a sigma algebra.
Yeah.
Because
We do this for every countable ordinal, and then we take the union of all of them.
yeah, well, actually, this one contains the closed and this one contains the open.
Oh,
Yeah,
So
but
the last, yeah.
what does it mean to say we do this countably to the first ordinal? What does that mean?
I should open a lecture about ordinal numbers. So let me say that, as I said, you have to do it countably many times.
Okay, but how is it?
Well, it's
what do we add when we say ordinal? When you introduce ordinal numbers here?
what is an ordinal number?
No, not.
No.
What do we gain by saying ordinal numbers here? So
but the fact that it is countable. So it is an explicit representation. And now you have that, you have a fine description of a set. Because, for example, if you know that in many theorems, you need to know that the Borel set that you are studying belongs to one of these classes.
oh, okay. So we
But this is a very refined, so it's a pointwise description of the set. So you know how many operations you have to go to arrive there.
oh, okay. So the ordinal numbers are just for ordering.
The ordinal number, yes, because it tells you exactly the ordering of the operations.
Okay.
So this is transfinite recursion.
No, it's
Transfinite countably, transfinite,
yes,
but countably.
Count, yes. And so there is a way to describe explicit the set. We don't care.
For example, if we have G delta 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 infinitely many times and F sigma 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 infinitely many times, we want to take the union of those and become a brand. So that's why we don't.
Is delta delta delta?
Yeah. Sorry.
The union or intersection.
So I start with an open set.
Yeah. A family.
Yeah, a family. I take their G's. Okay.
Okay. So the family is a family of open set which are described by, well, how many operations you have, no?
Yes.
So they are defined by essentially the index we described in which. So because the ordinal number tells you that you hold intersection, union, so union, intersection, union, intersection,
yes.
union, intersection, until this. And now you have the parameter. And so you put here a number of parameters. And these parameters should be counted. We have only counted many sets. So essentially like this. And then you do the intersection. So every set is represented by, you said, a countable family of open sets. And then I take complementation, intersection, doesn't matter. So union, intersection, it is perfectly described by the omega
yes.
and the index here. And this is indeed, you see that once I do and further operation, which is the union of the intersection, is just I increase by 1
yes.
my ordinal number. And that's why it's countable, because I mean, you never go to uncountable. The first uncountable is the union of all the countable ordinal numbers. But this is very big. Okay, this was just, you can forget everything, just to say that there is a way to write explicitly the sets. And this is useful when you want to know the regularity of the set. Okay. I'm a little bit slow here.
Do you ever get to the point where we need the ordering, or need to have the explicit description?
It depends on the question you have to answer.
Okay.
For the question we have to answer, no. But maybe in some cases you are applying a function to a Borel set, and the function has some regularity, and the Borel set needs another regularity in order to get the third regularity.
Okay.
So, for example, a typical case is when, for selection principle, you have a set, you want to find a function which lives in this set, and you want this function, which is the regularity of this function, and maybe it belongs to one of these classes. And then you say, usually is this class here, but actually sometimes no. Okay, so another problem which I forgot to say is that M is defined by M star restricted to the measurable sets. So we prove that M is a measure. M is translation invariant. Simply because M star was translation invariant, so the restriction is certainly translation invariant. And we have the meaning a measure is countably additive. Okay. And now we do something. Okay, so now we want to ask, the first thing is, let's say the regularity. So this is true, but what is the difference? Because the Borel set essentially is something that, as I showed you, more or less you can build, while the Lebesgue set you cannot, unless you assume the outcome of choice. So it's a complicated object. So let's prove the following theorem. Oh, we got the time. Okay. Still half an hour, no? Yeah. Because that clock is wrong. Inner,
1 hour.
outer, regularity.
1 hour change.
Yeah. So So equilibrium. E measure. E belongs to the basic margin. There exists G delta set such that the G delta set, let's say G, such that M star, sorry, E is contained in G and M star of G minus E is equal to 0. There exists, well, that's for all epsilon, there exists open E is contained in O and M star of O minus E is less than epsilon. And this is the outer regularity. And now we'll do the inner regularity.
Excuse me, here in the second condition we say that there exists a G, a delta set, and
G.
we call it G.
Yeah. And now there exists, I should have switched. For some reason I wanted to write. So for all epsilon, there exists C closed G, E is C is contained in E, and the outer measure of E minus C is less or equal than epsilon, less than epsilon. And finally, there exists F delta G, so G F sigma set. F is contained in E, and M star of E minus F is equal to 0. And this is the inner regularity. So essentially, if you have a measurable set, well, outside, up to a set of measure 0 is a G delta set, and up to a set of measure 0 is an F sigma set. So the answer to the question, what is the difference, are Borel sets, because F sigma G delta are clearly Borel sets, plus set of measure 0. So let's put it here, corollary. So L is B plus the sets of measure 0. Okay.
And what is the name of the theorem again? Inner outer regularity?
Inner or usually what is important is usually when a measure is set outer regular if can be approximated from outside by open sets. And inner regularity can approximate by inside by closed sets. And sometimes even by compact sets. But clearly you cannot get this epsilon here. I mean, you have just the measure approaches. And that's the two definitions. And okay, the book decided to call it inner outer regularity as a theorem, because here we construct and so we prove the proof. Actually, in general, this holds for almost all measures. When you don't have this one, you have it. Okay, so let's prove it. Let's prove this theorem. I need to. Okay, we prove just these 3 points, the equivalence of these 3 points. Why the other are the same? Because of complementation, no? You see that this is just the complement of these statements applied to the complement. You agree? If I take a set, I take the complement by this one, and I get the complement of this G will be F, the complement is O will be C. So let's make a picture. If this is E, okay, this is the set O, and this is the set C. The complement of C will be the open set for the complement of E, and the complement of O will be the closed set for the complement of E. So just need that first step. So I cancel this guy. So is in L, then there exists an open set such that is called. And for all epsilon, such that E is contained in O, and the outer measure of O minus E is less than epsilon. Okay, proof? Up to you. Let's start with the definition of outer measure.
We take the union of the covering.
Yeah?
It would work. It would be an open set, so it would work.
Yeah, but then you have one inequality where you have the, so you have the M star of E.
No, if we have an epsilon, by definition of the infemal, we get an
So you find M star of O, you find that E is contained in O, M star of O is less than M star of E plus epsilon.
Yes.
Then E is measurable.
yes.
That's the trick. Because I have that M star of O is equal to M star of E plus M star O minus E. Measurability. Okay, so this is less than epsilon E plus epsilon, so they get this one. So this one plus this one implies that this guy is less than epsilon. Yeah, nothing, but actually we can use N. Okay. Second to third. There exists for all epsilon exists O such that implies there exists F G delta G such that.
We take a family of open sets that converts to the outer measure, and we take the intersection.
Okay, so from here I take G is the intersection of the I of, for example, let's say O to the OI, where M star, so I have that OE is contained in OI, M star, OI, sorry, the I is below, minus E is less than E to the minus I as a matter. Probably goes to 0. Okay. Then, okay, this is trivial. And what is M star of G minus E?
It's contained in every one of those.
Less or equal than 2 to the minus I for over I.
So it must
Because
be zero.
it's contained in this one, no? Okay. From this to that guy, this is what we use already. Sorry, from this guy to E. And then I cancel. So there exists G delta G, then E is measured. We have used it also today, no?
You have what?
We have used the property that we are going to apply here already, earlier, in the first proof. That the intervals are measurable, and then we observe that, yes.
Yes, if the intervals are measurable, then so is countable intersection.
So these are measurable.
So
Then-
open sets are measurable, so their intersections are measurable.
Yes.
Is exactly, but then how to use it? So I don't know. There are several ways. I just think as follows: E is equal to G minus G minus E.
Okay.
Okay. So is this measurable?
This is
Yeah.
measurable, yeah.
Is this measurable?
It's measure 0, so it's measurable.
And then this is an operation because it's the intersection with the complement. So it's out. Okay, so in and outer regularity. Okay, now this cite this, but I think they cite it here, but it's an exercise, in my opinion, and then we do as an exercise. It's stated like it here. So if E is measurable, and the measure of E is less than plus infinity, then there exists a finite family disjoint intervals such that M of E, the symmetric difference with respect to the union, is less than epsilon. So for all epsilon, there exists a family so I should write then for all epsilon, there exists a family such that is whole. Okay, in my opinion, this is an exercise. In my opinion, this is an exercise. It's not a, it does not serve proof, but indeed I want you to do that. Okay.
We can do it like an exercise.
No, yeah, but we can do it now, just for fun. Okay, so starting point.
We write what is the symmetric difference.
We find an open covering of E with intervals, then we try to
Always
make
that.
it finite.
Well, starting point is always that one. So it's finite, then there exists.
Oh yeah.
Now this open covering, so it's a K in N such that. So it's disjoint, there are intervals such that E is contained in IK and in the union, sorry, and the measure of the union of IK is less than the measure of E. Okay, I need to spend epsilon half, no? Because the other epsilon will be spent when I cut.
Yeah.
Okay, now let's do the cut.
The cut. We cut using convergence.
Yeah.
They,
Yes,
this,
they are disjoint. So
the
this
Taylor
guy
series
is the sum of the length of IK. So I write this as the sum up to n plus the sum from n plus 1, and then such that this guy is less than epsilon half. that done? Yeah, done. For everybody? Or still you don't see what is the trick? Let's make the picture, then we understand. So, let's say this is the set. Now I take the covering. So the set is this guy. I take the covering. I cut the covering at some point. So what is now this difference? This difference is these tails plus this other tail, no? This other tail is controlled by which one? So let's put arrows. This one controls which part?
The part outside the bracket.
This one, no? And this one controls the part inside. And then you get upside. Okay. Now let's see some exercises which are very okay, a good question is this one. If E is not measurable, where this proof fails?
Where what?
If now E is not measurable, where does this proof fail? Just think.
We don't have the cover to start with.
Oh yeah, why not?
We have.
We have, by
We have
definition,
cover.
water measure.
We don't have something that I didn't.
Can we control it then?
But I don't. Okay,
No,
let's
we
the
don't
picture.
have
So
a-
we have. Let's say one piece is this one, and the other pieces are the intervals outside. Okay, which piece are maybe we can control? Which pieces can be controlled?
But the point, if E is not measurable, how do we get these intervals?
Because if M star
fair,
fair,
fair.
is the infinite. So which piece can make trouble?
Yes, we use the properties that because these are disjoint intervals, we can distribute the measure over the union. It becomes a sum. But in this case, we can't use this.
No, because we know that we have the proof that if this is measurable, the measure of A intersection, the union is equal to the sum of the measure A intersection each set.
But before this step, we did this for infinitely many. This only is true for measurable.
But actually, yes, but you see, the tail is already controlled by the sum, it's not the data point. The point is it's out here. So the measure of this guy is not the measure of the whole minus the measure of the one inside. That's the point. We use this as a trick because we say the measure of this difference is the measure of the sum minus the measure inside. But this, you see, when there is a minus, we cannot use plus. I cannot invert. I can invert on for measurable sets. Okay. So, well, this is easy. E measurable is equivalent to, for all epsilon, there exists O open, C closed. E is contained in C, contained in O, and the measure, well, actually here you can use the measure. O minus C less than epsilon. Trivial or not?
Because we can apply the inner outer with epsilon over 2.
Yeah, there you go. What it is? Assume that there exists f measurable, and f is contained in E and m star of E minus f is equal to 0. Then is E measurable?
Yes. Because E is.
And then the other one. Do the same in the case G contains E. G is in L m star of G minus E. Sorry, this already did, sorry. This is because I copied, but it's not what I wanted. I already gave the proof. I'm sorry. Is equal to m star of f. I'm sorry. I already gave the proof. And now it's the opposite. It's the same from outside.
Yes, but because f is a subset of E, we can use the monotonicity, so the outer measure of f is smaller than the outer measure of E, and we have, by this condition,
Yeah. You have to use always the sum to say that something is 0.
Okay, so
Okay. Have fun.
okay, we can use the fact that f is a G delta union a set of measure 0.
Yeah, at the end that's the trick.
This way E would.
Okay, just I don't want to spoil the surprise. The fact is that in one of the two you have the sum, and the other you should subtract. The subtract is false. The sum is true. So which one?
Okay.
Let's see the last one. Okay, just that there are other exercises, but let's put just each one. Which is something you have to think. Find m star star of a set of E is equal to the supremum actually is related to this exercise. M of f contained in E closed.
excuse me, here we have equal also the second one, or less than one?
Equal. Yeah, also equal. So essentially you have an outer set with the same measure and an inner set with the same measure. Which one is the good one? So prove that m star star is less than m star. So this is what is the inner construction, no? This is the outer measure and the inner measure, you can say, something built from inside the set. Then B is does equality hold for all sets? So these two are clearly related, no?
I don't think it's true in general.
Yes.
We have to have measurability.
Yes.
They're equivalent in some way.
For measurable sets, they would be.
Yeah, of course.
We've proven that they're equal in measurable sets.
Yeah. And non-measurable?
Yes, non-measurable sets can in principle be approximated from inside but not from outside or vice versa. So for this kind, yes,
Is written here.
yes, it depends on about which one is right.
Exactly.
Okay, so
Okay, so I have to go.